My name is Tricia Dunlevy, and this is my Lab 7 for Physics 2. The main objective with this lab was to use a star's position data given to us to model its motion due to gravitational force from a black hole, and then to find the magnitude of this force from the model, and use this to find the mass of the black hole. So my result was that the mass of the black hole was equal to 3.326 times 10 to the 31st kilograms. So to set up my system properties for the VPython model, first, I changed the mass of the star to 1.989 times 10 to the 30th, which was given to us as the mass of the star, and then changed delta t to be equal to 86,400 seconds, which is the length of 1 day in seconds. So then the next part of the code was to calculate the velocity from the data. So every set of data points that came from the graph, that came from the information, was calculated. A velocity was calculated. So delta x was equal to the x position minus the previous x position, and then the x velocity was equal to delta x, which is the change that was previously calculated, divided by delta t, which was the length of 1 day. And it's the exact same process for the y velocity. Then we use this information to calculate the net force. So we set v initial equal to the velocity of x for the first and velocity of x and y put together for the first index, and then velocity, we set the final velocity equal to the velocities we found before of the next index. And then P initial is just the star's mass times the initial velocity, and P final is just the star's mass times the final velocity. So delta V is just V final minus V initial, and delta P is just P final minus P initial. So then for dP dt, this is the change in momentum over change in time. So it's just equal to delta P over delta T. And then by the momentum principle tells us that dP dt is equal to F net. So we set F net equal to dP dt. So then we start to calculate the parallel component. And first we find that p hat is the normal vector in the direction of p, the momentum. So this is equal to the final momentum, because we're using that as our momentum in this case, divided by its magnitude. And that gives us p hat. And then the magnitude of the parallel component of the change in momentum dp dt is equal to the change in the magnitude of p, so it's magnitude of p final minus the magnitude of p initial, all divided by delta t. And then that just gives us the magnitude of the parallel component, but to find the actual parallel component, we have to take the magnitude multiplied by p hat. And this gives us the parallel component of dp dt. And again, the momentum principle tells us that the parallel component of F net is equal to the parallel component of dp dt. So we just set that equal here. And then we know that the change in momentum dp dt is just the sum of its perpendicular and parallel components. So we can easily calculate dp dt perpendicular by just taking the total dp dt and subtracting the dp dt parallel. And again, by the momentum principle, we know that F net perpendicular is equal to the change in momentum, or dp dt perpendicular. So then when I ran the module, it modeled the star's motion, and you can see that the star moves in an elliptical orbit. And we know this is a realistic model for the star's motion because it is elliptical, and the net force is always pointing towards the black hole, which is a realistic representation of the gravitational force. So to calculate the mass of the black hole, I first had my VPython program print out the F net so that I could see and use this for my equation. So I chose to use the first time interval just for simplicity's sake, so it'd be easy to find. So this is the net force I ended up using, the first line. I then found the star's position data for the same time interval from the star data file. And I know it is the second point because the first row represents the time when t equals 0, but we found the net force after 1 day. So the position we're looking for is represented by the second row. So 1.808 times 10 to the 12th. And then I found from my printout from VPython that the force of gravity was equal to this vector, as I just showed you. And then again found the magnitude of this force in the same way to be 1.328 times 10 to the 27th. So the formula for the force of gravity, the gravitational force, it's my process of finding the mass of the black hole using the position data from the star data, the position of the black hole given to us. I used this to find R and the magnitude of R, and then I found fgrav from the VPython printout, and again found the magnitude of this. And then I used the formula for gravitational force, for the magnitude of gravitational force, rearranged it so that I could find M2, the mass of the black hole, and then plugged in the values, and to get the mass of the black hole to be 3.326 times 10 to the 31st kilograms. So for the what does it mean problem, so when I ran the module, you saw the arrows representing the forces. The red arrow is the net force pointing towards the black hole. The blue arrow is the perpendicular component of the net force, and the black arrow is the parallel component of the net force. And these are related to dp/dt, dp/dt parallel, and dp/dt perpendicular, in that they have the same values by the momentum principle. But these quantities are fundamentally different in that we find them in completely different ways. The net force is the sum of the forces acting on the object, while the dp/dt is the change of the object's momentum over the change in time. So they're really different quantities, but the magnitudes or the values are equal to each other, and we find them in totally different ways. So if the black hole in our problem was replaced with a different black hole, but the motion of the star did not change, and we know that the motion of the star is only affected by the gravitational force of the black hole, then that tells us that the mass of the new black hole is not different than the mass of the original black hole. Because if the gravitational force is the only thing acting on the star, that's what's determining its path of motion. So from that path of motion, we can find the gravitational force, which is going to be equal to what it was before, which means that the mass of this black hole will be the same as what it was before.